the living organism. And this flies in the face of the traditional ways in which we think about chemical reactions. When we do reactions in our chemistry laboratories, we're typically using this kind of a reaction vessel. It's a round bottom flask where the chemist can control every single parameter of that reaction. By contrast, if your goal is to do chemistry in a living system, as was our goal, you're no longer in the reaction flask and you no longer have control over all of the parameters. Instead, you might be doing your chemistry in a live cell, in a cell culture dish, for example. And there are a lot of interesting problems you could solve by doing chemistry in the live cell. For example, to attach imaging probes to biological molecules that you want to study in their native habitats. And that's a very complex environment in which to think about chemistry. But even more complicated is the chemistry you might want to do in living organisms, like a laboratory mouse, or, as I'll show later in this talk, the zebrafish, which is a model for development of vertebrates. And probably the highest level of complexity where one might want to do a chemical reaction is the human. And in fact, as you'll see, bioorthogonal chemistry is actually now being tested in human cancer patients for the purposes of drug delivery. So for all of these kinds of reaction vessels, we knew that we needed a different brand of chemistry. And so we coined this term, bioorthogonal, to describe the qualities that you would need to do chemistry in these living systems. So our definition is that bioorthogonal reactions are reactions among components that neither interact with nor interfere with a biological system. And one way to think about that is that there is an enormous reactivity space that's described by biology. I like to think of biological reactivity space as a galaxy of chemicals within a much larger universe of chemicals. And it's a large galaxy, but there's a boundary around it. And somewhere outside of that biological reactivity space is the bioorthogonal reactivity space, a different galaxy with different chemicals, functional groups that you would not find in a biological system, but that will react with each other regardless of being surrounded by all of those biological functionalities. So that's the type of chemistry we'll be talking about today. Now, as I mentioned, chemical biologists often develop new technologies in response to an unmet need in biology. And in my lab, the unmet need that we became interested in was to study changes in cell surface glycosylation. That's another word for the complex carbohydrates that decorate the surface of all of our cells. And even back in the 1990s, there were decades of literature showing that when cells undergo a transformation of their state, there are changes in the patterns of cell surface glycans. And sometimes those changes in cell surface glycosylation are associated with disease. For example, it was already known back then that when healthy cells transform into a cancerous state in the context of a tumor, there are cell surface glycosylation changes that often include an overproduction of a particular sugar that's known as sialic acid. And it's one of the building blocks in the complex carbohydrates on the surface of your cells. And we had a fairly straightforward objective, which was to develop a technology that would allow us to profile the abundance of sialic acids on healthy cells compared to cancer cells, and to develop a strategy for molecular imaging of changes in sialic acid in order to study cancer. But at that time, there was no technology available to image cell surface sugars, including cell surface sialic acids. So that was the unmet need that we were focused on solving. How do you image a sugar? Well, you have to do it in a different way than you would image other biomolecules, like proteins or nucleic acids. For those other molecules, there were some good technologies available at the time, but for sugars, there was not. And during my postdoctoral years, so this takes me now back to around 1991 or 1992, I was thinking about this problem, the need to image the cell surface sugars. And I happened to attend a conference in Southampton, England. And this was a serendipitous moment for me because I heard a lecture by the late Professor Werner Reuter, a very well-known German biochemist at Free University Berlin. And his lab had been studying the biosynthetic pathway that produces sialic acids and delivers them to the cell surface. And what he had observed, and he presented this at this conference, is that one could feed cells a chemically altered version of a metabolic precursor of sialic acid that's called N-acetylmanosamine. And normally, N-acetylmanosamine has an acetyl substituent here at this pink position, where this R group would be a methyl group. And what he found is that one could make conservative changes to this R group, just extend the side chain out by a few carbon atoms. And those subtly altered N-acetylmanosamine derivatives would be subject to enzymatic metabolism inside the cell, which led to the production of an altered sialic acid residue, which was then incorporated into the complex carbohydrates on the surface of those cells. So you feed the cell a chemically altered sugar, and they produce a chemically altered sialic acid. And when I saw that talk, a thought came to mind, which was that maybe we could put a chemical group that's reactive at that position. And once that chemically reactive group appears on the surface of the cell, we could chemically attach an imaging probe. So that was one of the research proposals that I crafted and submitted when I applied for a faculty position at UC Berkeley. And here's a cartoon that's almost literally right from my job application from 1994, where I proposed a two-step process for imaging cell surface glycans. The first step would be to feed the cell or the organism, or maybe the human patient someday, that chemically altered simple precursor sugar. And that sugar would be metabolized by the cell, converted to the cell surface product, where this chemical group X, and I was agnostic about X at that time because I wasn't quite sure what X would be, but some chemical group X would come along for the ride. Now it's presented on the cell surface, and we would do a chemical reaction with an imaging probe that had a complementary functional group Y. And the hope was that X and Y would react with each other, form a bond, and that would attach the probe to the sugar, and we would now be able to image the sugar. But there was one problem with this cartoon, which is that we would need a chemical reaction between two functional groups that could proceed in a living system, in cells, in animals, the natural environment of these cell surface sugars, which means that the chemical reaction would have to be bioorthogonal. And this was the problem that was the genesis of bioorthogonal chemistry. So the reaction that we started with, and which ultimately was the first bioorthogonal chemical reaction, was a derivative of a very well-known chemistry from the German literature of the previous century. This is the classic reaction of triphenylphosphine with what turned out to be a very important functional group. You'll hear a lot more about this in the other talks this morning, which is the azide. And phosphines and azides will react with each other to to form an adduct called an azaylid. This was a chemistry first reported by Hermann Staudinger over 100 years ago, 1919. And in fact, Professor Staudinger won the Nobel Prize in Chemistry about 40 years after this initial report. Now, phosphines and azides do not exist in biological systems, and they react with each other very selectively without any interference by the biological system. So on its face, this reaction, as I've shown it, looks like it could be a bioorthogonal chemistry. But there was one liability with this classic Staudinger reaction, which is that the azaylid product is not stable in water. And if you're doing reactions in living systems, water is your solvent. There's no choice. So we had to solve this problem of the hydrolytic sensitivity of the azaylid. And one of my graduate students, Eliana Saxon, who joined my lab around 1998, came up with the solution to the problem. She made a simple modification of triphenylphosphine, introducing this methyl ester. So now, when the phosphine reacts with the azide to form this azaylid, the nitrogen atom, which is nucleophilic, can attack the ester in an intramolecular reaction, very rapidly forming this cyclic product. So now, when water ultimately hydrolyzes this phosphorus-nitrogen bond, the amide bond that had formed in that intramolecular reaction keeps this product together as a ligation product. So this variation on the classic Staudinger reaction, we called the Staudinger ligation. And this was the first example of a bioorthogonal reaction. And here is Eliana. I found this old photograph. The day that she got her first big result, where she showed the Staudinger ligation could be performed on cultured cells in a dish with no harm to those cells. And she came into my office and she showed me the data, and I remember thinking, I think this is a really big result. But this was very early in the days of my young lab. So once we had this chemistry worked out, we then demonstrated that we could introduce the azide into a variety of different cell surface sugars, all of which are interesting in their own ways. So for example, I mentioned that imaging sialic acid was one of our initial goals. And so we showed that we could introduce the azide on the side chain of N-acetylminosamine. And when fed to cells and metabolized inside the cell, the corresponding azidosialic acid would appear on the cell surface, primed for reaction by the Staudinger ligation. And likewise, we figured out how to put an azide into a sugar called fucose, which is also an important sugar for various biological systems. And in addition, we showed that we could put azides into N-acetylgalactosamine, or GalNAc, using this azidoacetyl variant of the parent sugar. And each of these sugars we chose because there were some interesting biological stories behind them. Another big moment in the lab came when two of my former graduate students, Jen Prescher and Danielle Dubey, demonstrated that the Staudinger ligation could be used to attach probes to sugars in living mice. This was another big moment in the lab because it was the first demonstration that a bioorthogonal reaction could be so well tolerated by a living system that you could do the chemistry in the mouse with no toxic side effects. And in fact, Jen and Danielle, I'm so privileged to say, are with us in the audience today. And here is an image from this paper they published showing that they could inject into mice azidoacetylminosamine. It would get metabolized by the cells in the body of the animal, and the azidosialic acid would appear on the surface of those cells. Then, in a second step, they would introduce a phosphine probe set up for the Staudinger ligation. And in the body of the animal, the phosphine would find the azide, undergo the reaction, and form this product, which we could then detect in a variety of ways, including with fluorescent-tagged monoclonal antibodies. Another major achievement by these fearless students who were willing to turn the mouse into a reaction flask. But we knew that there was more work we had to do in reaction development. And the reason was that the Staudinger ligation, for all of its amazing qualities, was a rather slow reaction at biological temperatures. It's a bimolecular reaction, which means that it follows bimolecular reaction kinetics. And so hopefully the students in the audience will recognize that for such a reaction, the rate is equal to an intrinsic rate constant times the concentration of the two reactive partners. And in a biological system, like a living animal, we learned some things that are important. For example, we learned that the concentrations of these reactants were probably going to be very low. The animal is metabolizing these reagents as soon as we put them in the body. This is not a reaction flask in your fume hood. And there's only so much of a molecule you can introduce into an animal because of issues like solubility in aqueous systems or non-specific toxicities for molecules that really don't belong in the animal's body. So given the limits on the concentrations of these two parameters, the intrinsic rate constant of the reaction is very important if you want the reaction to proceed at a reasonable rate. And for the Staudinger ligation, which had a second-order rate constant around 10 to the minus 3 per molar per second, we discovered that this was a little too slow. This reaction took hours to proceed, sometimes a day. And there's a lot of biology that takes place on a much shorter time scale than a whole day. So we were interested in alternative bioorthogonal reactions that would leverage the azide as a reactive partner. Now it turns out that azides can also undergo what we call 1,3 dipolar cycloadditions with alkynes. This is another chemistry that was well established in the previous century. And Professor Rolf Huisken from University of Munich was one of the major practitioners of this chemistry, who did a lot of mechanistic work to describe how this reaction proceeds. And like the classic Staudinger reaction, this chemistry seemed to us as being almost bioorthogonal, because like the azide, alkynes are also quite rare in biological systems. We don't have them in our bodies, as far as we know. And yet these two will react with each other to form a product called the triazole. Now the reason I say this is almost, but not quite, bioorthogonal is because this reaction is very slow at room temperature, much slower even than the Staudinger chemistry. Which is why when people do these reactions in the fume hood, in the chemistry lab, they generally have to reflux the reaction at high temperatures, like 100 degrees C. So at biological temperatures, we thought of this Huisken chemistry as just being too slow for our needs. Now in 2002, the world was changed. And that's because my co-laureates, Professor Barry Sharpless and Professor Morten Meldal, discovered a mechanism for accelerating the rate of the azide-alkyne cycloaddition. And this is what is now almost synonymous with the term click chemistry. And as you will hear from their glorious lectures after mine, the addition of a copper catalyst changes everything. And suddenly, this reaction is incredibly fast. It's over in minutes. And it is now by far one of the most important reactions in all of chemical biology, and very much worth recognition by a Nobel Prize. Could this solve our problem of kinetics? And the answer was not quite. The problem was the copper catalyst was just too toxic for cells and live animals. But it was kind of on the right path, and it got us thinking about other mechanisms by which one might accelerate the rate of the cycloaddition, but without the need for a toxic metal catalyst. Now, like many of us, I teach sophomore organic chemistry, introductory organic chemistry. And when we teach this class, we always have a lecture on the concept of ring strain. And here are the two textbooks that I used to use to teach this class when I was at Berkeley, both written by Berkeley faculty, Peter Volhart, Clayton Hethcock, and Andy Streitweiser. And in these books, you will see a description of what happens when you make ring systems that have uncomfortable bond angles. These strained ring systems can cause functional groups to have very different reactivities. So for example, when you put a double bond into a three-membered ring in this form or in this form, a lot of strain energy gets pent up in that ring. And if you can react those pi systems and release the strain, that can accelerate the rate of a reaction dramatically. So I talked with my students about whether there was precedent for an azide alkyne cycloaddition with a strained ring system. And Nick Agard, who is sitting here in the audience today, went to the library, which used to exist, and he found this amazing precedent. Back in 1961, Georg Wittig, another Nobel laureate in chemistry, reported on the reaction of cyclooctane, the smallest of the stable cycloalkynes, which has 19 kilocalories per mole of strain energy. And when Wittig and Krebs, his coworker, combined cyclooctane with phenylazide, you can see from this statement in German, the reaction proceeded like an explosion to form the corresponding triazole. So here was an azide alkyne cycloaddition with no catalyst that basically proceeds at room temperature without the need to heat it up. So based on that precedent, Nick and then Jeremy Baskin, who's now a professor at Cornell, and he's sitting here in the audience today as well as several other coworkers, went to task to try to develop cyclooctane-based probes for what we called a copper-free click chemistry that we could use in living systems. And to make a long story short, they spent several years building cyclooctanes with different kinds of modifications. And what we learned is that the cycloaddition of these cyclooctanes with azides can be tuned in terms of reaction kinetics over several orders of magnitude. So we had a lot of control levers on the rates of these cycloadditions. Just to give a few examples, in the upper left is a very simple cyclooctane, which would react with a model azide with a second order rate constant that was kind of on par with the Staudinger ligation. So that was our starting point, but we knew that we needed to enhance the rate by a few orders of magnitude. And so Jeremy Baskin had a big breakthrough in this project when he showed that addition of 2 fluorine atoms next to the triple bond would increase the reactivity almost 100-fold. And this reagent, which we gave the acronym DIFO for a difluorocyclooctane, became one of the first important reagents for imaging sugars in live systems, as I'll show you next. But just to complete the slide a little bit, we could enhance the rate yet another order of magnitude by fusing benzene rings on either side of the cyclooctane, which increases the ring strain even a little bit more. And then the ring could be shrunk down to a 7-membered ring as long as one of the atoms in the ring was a larger atom like sulfur. And one could get yet another boost in the reactivity, where now we have a reagent that's 4,000 times more reactive than our parent compound. So this was a really fun period of time in the lab because we felt like we were returning to our roots as physical organic chemists, doing the kind of structure reactivity correlation studies that were popular 100 years earlier, but that had fallen out of fashion in the new millennium. And yet here we are invoking some of these classic concepts to tune a reaction for biological systems. With these new reagents in hand, Jeremy Baskin and another coworker, Scott Laughlin, took on the challenge of imaging sugars in live animals. And the animal that they focused on was the zebrafish, which is a very popular model organism to study vertebrate biology, with the benefit that zebrafish are translucent. So they're a wonderful organism for fluorescence imaging studies. You can see all of their organs under a microscope as they are alive. And so Jeremy and Scott did experiments where they would take early embryos of zebrafish, developing in a dish. They would feed these embryos azido sugars, which would get metabolized. And once those azido sugars appeared on the surfaces of the cells of the animal, they would do the copper-free click chemistry reaction in the live animal with a dye-faux probe, introduce the fluorescent dye, and now we could image the sugars for the first time in a living animal. It was a very dramatic moment in the lab. And they did some experiments where they would pulse these embryos at different time points with different azido sugars and map out sugars appearing in different cell types. So for example, in one experiment, they would do one round of labeling, and then any unreacted azides still present in the fish, they would quench with a reagent that is a phosphine reagent in a classic Staudinger reduction. Then they could pulse the embryo with more azido sugars that would appear at different time points and label them with different colored dyes. And we could create fish that basically had all the colors of the rainbow, where the different colors represented different types of cell surface sugars that appeared during development at different time points. Just to give you a sense of what these images looked like, up top is the head of a roughly 5-day-old zebrafish, which has had different sugars labeled at different time points with different colors. And you can see how they're distributed. And below that is basically a round of cell division from an earlier embryo. So here's the intact early embryo. Each arrow is pointing towards cells that are undergoing mitosis. And if you expand the image and take a close-up look at cell division, what you can see is that a single parent cell, I'll wait for it to loop, duplicates its chromosomes, segregates them as the cells divide, and you can see the cell dividing through the portal of the DNA, which there are good tools for imaging, and we used one of those tools here. You could see the cell division through the portal of the proteins, which were also easy to image back then, and the proteins that we're imaging here are located on the membrane of the cell, and now it's dividing into two daughter cells. But for the first time, we could also see cell division through the portal of the cell surface glycans. And that was another first-in-class achievement by these incredibly fearless group of students. And in this image, we were quite struck to see how the glycans build up and concentrate right at the junction as the cell is completing a round of mitosis, and contributing to the segregation of these daughter cells in a way that was previously unknown. So after this point of time, the field really took off, because it turns out that once you show that you can use chemistry to image sugars in a biological setting where the animals are alive, lots of people came out of the woodwork and asked us if they could use our reagents to image all kinds of other kinds of molecules that were also difficult to study. And so here's a pie chart on the cell showing roughly the breakdown of all the different types of biological molecules. And over the course of 4 or 5 years, and this brings us up to about 2010, there were groups that showed that they could use the azide as what we call now a chemical reporter for virtually every type of molecule on the pie chart. They could put azides into amino acid side chains and label proteins, and use bioorthogonal chemistry to image those proteins in living systems. They could put azides into nucleosides and label the oligonucleotides, and use bioorthogonal chemistry to image those molecules. They could put azides into lipids and track those lipids around in living systems using bioorthogonal chemistry. So the applications of this chemistry in the research setting expanded quite rapidly into lots of different areas of biology. Another big development around that time was expansion of the toolkit of reactions that are available for bioorthogonal chemistry. And so we started our work with the azide, and the cyclooctane partner became a really good combination for chemistry and living systems. But later, other groups discovered that tetrazenes can be bioorthogonal reagents reacting with strained alkenes like this cyclooctene or this cyclopropene. And now that toolkit continues to grow, and I would put the challenge out to students in the audience here. If you come up with a new idea for a new bioorthogonal chemistry, this could have tremendous impact. Because while we now have a handful at our disposal, there's always a need for more options in this space. It's a great challenge for someone who's starting out their career in organic chemistry. Also, the applications expanded. So 20 years ago, we developed these chemistries as tools for basic research in the laboratory setting. But over the last 10 years or so, there's been considerable activity in the translation of this chemistry for new medicines and new diagnostic strategies for human disease. And so I thought I would mention that there are now a number of biotechnology companies that use bioorthogonal chemistry in a variety of settings. A very popular application is for making antibody drug conjugates. And these are important medicines for the treatment of cancer. As well, there are companies that are using bioorthogonal chemistry to make new vaccine conjugates. And some of these are in, right now, a phase 2 clinical trial. And then I have a company, as a disclosure, which uses bioorthogonal chemistry to make targeted degraders of extracellular molecules. And I'm very excited to be an advisor of a company called Shasky, which is performing bioorthogonal chemistry in the body of cancer patients as a mechanism to target chemotherapies very selectively to the tumor tissue and to keep those chemotherapies away from healthy tissues. So it's a very exciting time for me to see how the chemistry came from a very modest idea in the research lab aimed at imaging sugar molecules into a very generally applicable tool which people are using to make new types of medicines. Finally, I want to make one point, which I think is important, because despite all of these exciting applications, I still think the most important lesson from the story of bioorthogonal chemistry has to do with the importance of curiosity-driven basic science. And those of us who are scientists are familiar with what people often describe as a tension between basic science and applied science. And funding agencies go through various phases of interest in applied science versus basic science. But bioorthogonal chemistry tells the story of how important curiosity-driven basic science can be in order to realize these applications. Because I'm pretty certain that the chemists on whose shoulders we built bioorthogonal chemistry, and by that I mean Hermann Staudinger, Rolf Huisken, Georg Wittig, when these chemists reported on the curious reactivity of azides, phosphines, and alkynes, they would never have foreseen that someday I would stand here and show you fluorescent zebrafish. They couldn't have known that. They made observations about exotic molecules and they published them purely based on curiosity. And here we are 100 years later making use of these chemistries in ways that we hope will benefit human health. So in order to get to fluorescent zebrafish and imaging of sugars, to imaging of tumors in human cancer patients, and to making new medicines, you need to have that foundation established by the basic science. So with that, let me thank the bodies of people that basically made this moment possible. First and foremost, the Royal Swedish Academy of Sciences and the Chemistry Nobel Committee. Thank you for changing my life. The Nobel Foundation for the amazing festivities of this week, which are just ramping up. My institution of origin, UC Berkeley, which we often call Cal, this is where all the work was done that I presented today. So I owe a great debt of gratitude to the students and to the faculty at Cal that gave me my big break and that did all this beautiful work. And my current institution, Stanford, is very supportive and is helping me try to translate some of these reactions into human medicines. And then finally, the people who financially supported this work from the very beginning, which is the National Institutes of Health and the Howard Hughes Medical Institute. The most important slide of all is this one, because none of this happens without the intrepid students and postdocs that occupy the academic laboratory. And this is my current group at Stanford. This is how we had group meetings during COVID. We had to rent a drone to get this picture. And after the Nobel Prize announcement, my students organized a Zoom party. And these are all the faces that we could get on Zoom on short notice from all over the world, and some of whom I'm presenting this work to today. Thank you very much for the work that you did leading to this moment, sitting there in the second row. My family is here. Thank you very much for all the support you have given me since my moment of birth. And thank you very much to this audience for coming today. Thank you.
Welcome to the Royal Swedish Academy of Sciences and this press conference when we will announce this year's Nobel Prize in Chemistry. We will keep to our tradition and start in Swedish and then continue the presentation in English. And you are of course welcome to ask questions later on in either of these languages. Jag heter Hans Ellegren och är ständig sekreterare här vid Kungliga Vetenskapsakademin. Till höger om mig sitter professor Johan Åkvist som är ordförande i Nobelkommittén för kemi. Och till vänster om mig sitter professor Olof Ramström, också ledamot av Nobelkommittén för kemi och sakkunnig inom ämnet. My name is Hans Ellegren. I'm the Secretary General of the Royal Swedish Academy of Sciences. And to my right is Professor Johan Åkvist, Chair of the Nobel Committee for Chemistry. And to my left, Professor Olof Ramström, member of the Nobel Committee in Chemistry and one of the experts in the field. Årets pris handlar om ett funktionellt sätt att bygga molekyler. This year's prize is about an ingenious tool for building molecules. Kungliga Vetenskapsakademin har idag på morgonen beslutat att utdela 2022 års Nobelpris i kemi i lika delar till Caroline Bertozzi, Stanford University, Kalifornien, USA. Mårten Meldal, Köpenhamns universitet, Danmark. Och till Barry Sharpless, Scripps Research, La Jolla, Kalifornien, USA. Det tilldelas priset för utveckling av klickkemi och bioortogonal kemi. The Royal Swedish Academy of Sciences has this morning decided to award the 2022 Nobel Prize in Chemistry in equal shares to Caroline Bertozzi, Stanford University, California, USA, Mårten Meldal, University of Copenhagen, Denmark, and to Barry Sharpless, Scripps Research, La Jolla, California, USA. They received the prize for the development of click chemistry and bioorthogonal chemistry. Professor Åkvist will now give us a short summary in English of the prize. Please, Johan.
Thank you. Click chemistry is almost like it sounds. It's all about snapping molecules together. Imagine that you could attach small chemical buckles to different types of building blocks. Then you could link these buckles together and produce molecules of greater complexity and variation. This was the basic idea behind click chemistry that Barry Sharpless had about 20 years ago. The problem was to find good chemical buckles. They have to react with each other easily and specifically. Mårten Meldal and Barry Sharpless independently found the first perfect candidates that will easily snap together, and importantly, they won't snap with anything else. This click chemistry can now be used for building drug molecules, polymers, new materials, and many other things. However, there are also other reasons for why one likes to snap molecules together. Imagine that you could attach a shining molecule to biomolecules in a living cell. Then you could follow them in a microscope and see where they are and how they move. This is what Caroline Bertozzi did, but she had to find click reactions that were not toxic to the cells. She called this bioorthogonal chemistry, chemical reactions that don't interfere with the normal biochemistry of life. This now allows us to attach all kinds of molecules to biological ones, which can be very, very useful. Besides tracking biomolecules, it can also be used for diagnostics, for delivering drug molecules to their targets, and many other applications. So this year's laureates founded the fields of click chemistry and bioorthogonal chemistry. It has led to a revolution in how chemists think about linking molecules together and how to do it in living cells. Thank you.
And I'll leave the word to Professor Olof Ramström, who will give a more detailed presentation of the prize. Please, Olof.
Thank you so much, Hans. Thank you, Johan. So this year's award is, as Johan just mentioned here, is about making connections between molecules in a very straightforward, selective, and robust way. This year's award is also about concepts and how concepts combined with very important discoveries really push the boundaries and make enormous impact of science and our society. So let's start with the first concept. Around the turn of the millennium, Barry Sharpless presented a new concept which he called click chemistry. And by this, he meant chemistry that was based on very special reactions that work very efficiently, were very reliable, and gave very robust products, very robust yields of products. By this type of chemistry, like Johan here said, you would be able to essentially click together two molecular building blocks in a very efficient way, in a very predictive way, and you will get a good amount of product in a very reasonable short time. Now, such reactions were not very common or very difficult to find. But one such reaction was just about to be discovered. And very shortly after this click chemistry concept was introduced, Morten Meldal and his group in Denmark, and very shortly after, Barry Sharpless and his co-workers in the US, they found one such reaction that is really remarkable. This reaction is based on an A-side functionality, as you can see to the upper left here. This is a structure which has 3 nitrogen atoms in a row. And the opposite candidate here, the opposite reactant, as we call it, is an alkyne, as you can see to the right. And this alkyne is a kind of structure where you have 2 carbon atoms that have 3 bonds between them, a triple bonded carbon. Now, these 2 reagents, these 2 building blocks, they are not terribly reactive by themselves. And if you mix them together, they will react very sluggishly with one another. And also, they will give mixtures, very often give mixtures of products. So not very good. However, what Meldal's group and Sharpless and co-worker found out was that if you add a little bit of copper 1 ions to this reaction mixture, the reaction was dramatically accelerated. And also, it only gave 1 single product. And the product is this ring-shaped, 5-member ring-shaped product called a triazole. And again, this product is also quite unreactive product, quite stable product. And it also has other interesting features that could be of interest. So in a sense, as you can see here, this particular reaction fulfilled the criteria of click chemistry. And now you had a tool where you can easily click together molecules in a very effective way. Immediately upon discovery of this reaction, this reaction is called, as you can see down here, the copper-catalyzed A-side alkyne cycler addition reaction. Immediately upon its discovery, it gained enormous interest across chemistry and related fields, and immediately spread across all fields. And now, with this reaction, it was now, and essentially, although other reactions have been, so to say, identified and discovered after this one, this particular reaction has almost become synonymous with the click chemistry concept. and is also often called the click reaction. And you can say that it's still the crown jewel of click reactions. And with this reaction, it's now possible to build together relatively complex structures, as the one you can see here, where you can click together multiple components, multiple building blocks, click them together in sequence or in parallel, giving rise to, in this case, a star-shaped complex molecule, dendrimer-type-like molecule. Now, one of the areas where people wanted to apply this reaction was in biology or biology-biochemistry related areas. But for this reason, in these cases, when you work with living cells, copper is not ideal, and living cells don't really like too much copper. So for this reason, alternative reactions were sought after. And that brings us to the second concept. Around the same time as the click chemistry concept and these copper-catalyzed click reactions were introduced, Caroline Bertozzi formulated a concept which she called bioorthogonal chemistry. And by this, she meant chemistry that is based on special reactions that can be performed in living systems, in living cells, in living organisms, without affecting or being affected by the myriad of substances and reactions that occur in such very complex systems. As you can imagine, this is definitely not an easy task. So during the 1990s, Caroline Bertozzi had been trying to work out the chemistry and biology of complex carbohydrate structures, complex sugar structures that are called glycans, and they are often located at the surface of cells, as you can see in this picture. Bertozzi and her group had been identifying chemical reactions that could work in living systems, in living cells. For example, they had identified a way to introduce the A-side functionality in living cells and living systems. And they could do so by a type of metabolic engineering approach, where you have a sugar structure, a carbohydrate structure, which is then functionalized with an A-side moiety. And when you grow cells in the presence of this structure, this can be taken up by the cells, it can go through and be processed by the cell machinery, and finally become incorporated in the glycans that you find at the cell surface, as you can see here. Now, once this fantastic copper-catalyzed click reaction had been discovered, shortly after, Bertozzi could also identify a metal-free alternative. And you can see the alternative here. And this alternative was based on a so-called strained alkyne, as you can see. This is an 8-membered octagonal alkyne, where the alkyne's moiety is actually twisted in a sense that it becomes much more reactive. And this alkyne structure, you can then, of course, functionalize any way you want. In this case, for example, with a molecule that can emit green light. And if you then add this strained alkyne to the cells where you have this A-side functionality, these two components can click together very efficiently, and now you have labeled the glycans at the surface of the cell, and you can study where they are under the microscope. And that's exactly what you can see on the next slide here. Here you see a number of cells, and the blue part here is the cell nuclei that have been labeled blue. And you can see the green, shining green surface of the cells where you actually have those glycan structures. So these two concepts and the many reactions that have been, so to say, discovered, they have really had an enormous impact on science. And and there's many, many widely applied across all disciplines of chemistry and related sciences, neighboring sciences. Click chemistry, if you take click chemistry, has been applied almost everywhere. You need to very quickly connect two building blocks. For example, just to give you a few examples, it's been applied to pharmaceutical development, it's been applied to conjugation of various biomolecules, such as, for example, in DNA sequencing. It's also been applied, very much applied in material sciences, where people have been building very advanced and functional materials using these methods. When it comes to the bioorthogonal reactions, these have been heavily used to explore how biomolecules, the fates and the roles of the biomolecules in cells and in organisms. They have been used to study disease and deciphering disease processes, and of course that can then lead to the development of new drugs. And in a little movie you can see here to the bottom left here, we have one such example where you can see a bacterial cell. You can see the cell envelope is marked in green, and inside this bacterial cell, one of the proteins has been labeled using this kind of chemistry, and now you can follow it in real time inside the cell. So clearly, these very important accomplishments and these really fantastic discoveries from our three laureates have really made an enormous impact on chemistry and on science in general, and for that, it's really been to the greatest benefit of humankind. So, thank you.
Thank you, Olof. Det sa bara klick, as the Swedish quote often is said. Now we shall see if we have one of the laureates with us. Professor Caroline Bertozzi, are you there?
Yes, I'm here.
Congratulations for receiving the Nobel Prize in Chemistry.
Thank you so much, all of you. I'm absolutely stunned. I'm sitting here, I can hardly breathe.
I understand. It's the middle of the night for you. Was it a shock to obtain this call in the middle of the night?
Yes, that's an understatement. I'm still not entirely positive that it's real, but it's getting realer by the minute.
Yeah, it will probably be a long night for you today, I guess. We shall see if we have some questions here. I'm sitting in the session hall of the Royal Swedish Academy of Sciences, and we have many interested journalists here, both from the international press as well as from Swedish press. Are you ready to take some questions?
Absolutely. Hello, everyone.
Okay. SVT?
Good morning. Congratulations. This is Swedish television, public service. Thomas von Heine. We heard something about applications from your work. Could you say something? Could you add something to that? What, in your mind, the most interesting applications?
Absolutely. You know, to my mind, the two types of applications that I think are really making a lot of impact are, first of all, the use of bioorthogonal chemistry as a biological discovery tool to discover new kinds of biomolecules that we didn't even know existed because we have a new way to look at them. And then the other important area of impact is in medicine, and in particular for drug delivery, which is doing chemistry inside human patients to make sure that drugs go to the right place and stay away from the wrong place.
Okay, I think first we had a question here somewhere.
Congratulations, I'm Anneli Megner-Arn, Swedish TV4. I wonder if your click technique was involved when we were developing the antibody test of COVID-19.
That's a great question. we did some research in my lab around not so much diagnostic tests, but development of potential therapeutics to treat acute COVID-19. And we did use click chemistry and bioorthogonal chemistry in putting together some drug prototypes.
Okay, question in the back there.
David Keaton from the Associated Press. First of all, when we look at click chemistry today in 2022, what are the areas of new developments that you're the most excited about, the new discoveries? And if you could maybe explain in layman's terms what this really means to chemistry.
Thank you for a great question. I think the field of bioorthogonal and click chemistry is still, I think, in its early phases. We have a handful of incredible reactions like the ones that Professors Sharpless and Meldal developed. But it's really just a handful. And I think there's probably many new reactions to be discovered and invented. So that's an important frontier, is inventing new chemistry. And then in terms of applications, again, I think applications in the biotech industry, the pharmaceutical industry, and the development of new ways of treating diseases and diagnosing diseases, I think that these are areas that will be very strongly impacted by click chemistry, as they already have been.
Okay, question here, please.
Congratulations, Professor. Click chemistry is a very effective and useful method for building molecules. So my question is it easy to scale up the reaction?
Yes. In fact, I think that's one of the most elegant features of click chemistry reactions, is the fact that they're so simple and they're so highly selective that the yields tend to be very high with very little impurities, and that makes them very nicely scalable. And in fact, click chemistry reactions are already being performed at manufacturing scales in the pharmaceutical industry.
Okay, we have time for more questions. Oh.
Thank you. Pardon me, Philip O'Connor, the Reuters news agency. Congratulations, Professor. I'd like to ask you, was there a specific question that you were seeking an answer to when you set off down this path? And did you find the answer, or did you get answers to different questions in your research?
This is a great question. And the answer is yes and yes. And just to give you a little bit more detail, what set us down the path of developing bioorthogonal chemistry was an interest in being able to visualize molecules on cells that no one had been able to see before. And those molecules for us were the glycans. And once we figured out how to visualize the glycans using those chemistries, we learned all kinds of interesting things about the functions of glycans that coat the surfaces of cells. And what we learned led to the development of a new idea for cancer immune therapy, and at the same time also led to the discovery of a new kind of biomolecule called glycoRNA that had never been seen before. Does that answer your question?
Okay, one more question here.
Associated Press. Obviously, this prize comes with an incredible notoriety and also prize money. What do you think this notoriety will bring and this prestige will bring to this area of science, to yourself, and then obviously, what are you hoping to do with this, the prize money that comes with this?
I can answer your questions in reverse order. I haven't had enough time to think about the prize money, so I don't know yet. But then to your earlier questions, I think that the attention that a prize like the Nobel Prize brings can be incredibly energizing for a scientific field. And I've been very fortunate to work at the interface of chemistry and biology. It's such a rich interface with so much great technology development and fundamental basic science discoveries. And so to the extent that the prize casts a light on chemical biology, I think that's a wonderful thing. I think the other incredible benefit is that it's an opportunity for me to recognize all the work that so many trainees from my lab have done over the last 25 years. And I've been very blessed with an incredible team of graduate students and postdoctoral fellows and undergraduates and staff. And it's an opportunity for me to reflect on how fortunate I have been and to share in the celebration with them.
This seems to be the last question from the press for you, Professor Bartosi. Thank you, and once again, our warmest congratulations for receiving the 2022 Nobel Prize in Chemistry. We look forward to see you here then in Stockholm in December then.
Myself as well, and thank you so much.
Goodbye, goodbye. Let's move on to see if there are some questions here to the committee about the research or the prize. You have one more here directly.
Yes, a question about the comparison between last year's prize and this year's prize. Both dealt with new ways of building molecules. Is that correct? Could we say that there are bridges between these two prizes, or is that not the case?
Would you like to?
Well, they are separate areas, of course, but you're perfectly right in that it has this ingredient of different new ways of building molecules. Although last year's prize was maybe more a pure organic chemistry prize, as you have heard, this year's prize spans very big application areas in chemistry. So, but it's about building molecules and attaching molecules to each other.
More? Yeah, please.
This is Dongkun from Nordic Chinese Times. And again, one question is click chemistry a good method for conducting framework materials like MOF, metal organic frameworks?
Olo?
Well, that's an interesting question. And actually, I think it has been applied to that particular field as well. So you can introduce either the acide or the alkyne group, if you use that reaction, in this these organic frameworks that you're referring to. And then you can just click on the other reactant, and then you have a way to functionalize these frameworks very easily and straightforwardly. So yes, it has been used like that.
Are there any more questions? If not, we say thank you for your interest. We hope to see you back here in the Academy on Monday when we will present this year's Sveriges Riksbank's prize in economic science in memory of Alfred Nobel. Thank you.
Chemistry Prize Committee. This Click Prize, what is it about? Can you please explain?
This is a fantastic prize. This is a fantastic prize to fantastic discoveries, I should say, that our 3 laureates have made. And they have been working on methods to try to connect molecules, connect building blocks, and they can be clicked together very simply and straightforwardly. And essentially the same way as you build Lego, right? So you can have the Lego pieces and you can just click them together and you can build very advanced, houses or tools or vehicles, even spaceships you can build using that. And the same is the same with this chemistry, although at a very, very, molecular level, so to speak. Everything is very small, but you can click them together and you can build very advanced structures in a very simple and straightforward way.
And why has this been so difficult before?
Well, it's very difficult to find such means or such reactions, as we call them, to actually do this. Because if you want to have a reaction that can be really just work every time you use it, just clicking together every time you want to use it, and you get predictable products, you know what you will get. That is really difficult to do. Right? So there are not many reactions like that, and we only have a handful of such reactions today.
And what do you build with those click things? I mean, what could it be used for?
The funny thing, the good thing with these discoveries is that it can be used for almost everything. So it's been spread very widely. And it's been used where you, for example, make new drug compounds, to treat illness and so on. It's been used to make all sorts of different materials, like polymers, like gels. It's hard to explain what those mean. but you can make almost everything where you just want to click together things, right? You can build very advanced structures that can be used to deliver drugs in the human bodies. You can use them for almost everything you can think of.
And why did you decide to give the prize right now? Why is this moment?
Well, that is always a very difficult question to answer. But the way we work normally with many different areas at the same time. And in this particular case, this field has now matured in such a way that we now think it's ready for this kind of award. So now we have all the pieces of the puzzle together, you can say. So now we just know that exactly the last piece of the puzzle came in, and now we see that the whole picture is perfectly fine. And we have now a very fantastic new award, as we can say.
It's about time, you say?
You can say it's about time.
So tell us a little bit about the laureates. One of them, Barry Sharpless, he got the Nobel Prize 2001. Is this common?
This is not at all common. This is not at all common. It happened a few times before in the past that certain individuals are really, really, really creative, and Barry Sharpless is one of those. So he got the Nobel Prize in 2001 for a relatively different area. And now, after that, he has continued working on other things, for example, this thing. And he made such important discoveries in this field. So you have to say that he is a really creative person, and he deserves now this second award.
We just heard another one, Caroline Arbitruzzi on the phone. Could you tell me about the reaction when you called her?
Well, I cannot say too much, but we can say that when we call the laureates, they are always very, very happy. They're almost always very surprised, and it's a very emotional moment when we call them all the time, every time.
Are they related? I mean, do they have they been working together on this? Do they know each other? Could you tell us?
I'm absolutely convinced that they know each other, but I do not think that they have actually been working directly with one another. Might be. I'm not absolutely certain about that, but definitely know each other because these discoveries and the concept they have come up with, they are very connected.
для всіх держав та їхніх громадян, незалежно від участі у військових блоках, їхнього військового потенціалу чи економічної потужності. Права людини мають посісти у цій новій системі центральне місце. І це завдання не тільки політиків. Політики мають спокусу уникати пошуку складних стратегій, що вимагають тривалого часу. Вони часто поводяться так, ніби глобальні виклики самі колись зникнуть. Але правда в тому, що вони тільки загострюються. Ми, люди, які хочуть жити у мирі, маємо говорити політикам, що нам потрібна нова архітектура світопорядку. Можливо, у нас немає політичних інструментів, але в нас завжди лишається власне слово та власна позиція. Звичайні люди мають набагато більше впливу, ніж вони самі собі думають. Голос мільйонів людей у різних країнах може змінити світову історію швидше, ніж втручання ООН. Четверте. Як забезпечити справедливість усім жертвам війни? Диктатори бояться утвердження ідеї свободи. Тому Росія намагається переконати весь світ, що верховенство права, права людини та демократія – фальшиві цінності. Бо під час війни вони нікого не захищають. Так, право не працює. Але ми віримо, що це тимчасово. Нам належить розірвати це коло безкарності та змінити підходи до правосуддя за воєнні злочини. Стійкий мир, який дає свободу від страху та відчуття перспективи, неможливий без справедливості. Ми досі дивимося на світ через призму Нюрнберзького трибуналу, де воєнних злочинців засудили лише коли нацистський режим впав. Але справедливість не має залежати від стійкості авторитарних режимів. Зрештою, ми живемо у новому столітті. Правосуддя не має чекати. Нам потрібно подолати прогалину відповідальності та дати шанс на справедливість усім постраждалим людям, коли національна система перевантажена кількістю воєнних злочинів, коли Міжнародний кримінальний суд обмежується кількома вибраними кейсами або взагалі не має юрисдикції. Війна перетворює людей на цифри. Ми маємо повернути імена усім жертвам воєнних злочинів. Незалежно від того, хто вони, їхнього соціального статусу, виду злочину та жорстокості, яку вони зазнали, і чи цікавиться медіа та суспільство їхньою справою. Бо життя кожної людини має значення. Право – це жива матерія, яка постійно перебуває в розвитку.